There are a lot of things that we know about climate change. We understand how pollution of the atmosphere with greenhouse gases such as carbon dioxide and methane trap heat within the atmosphere and cause the surface of the Earth to heat up. In fact, it's been almost exactly 30 years since head scientists at NASA told the US Senate committee the greenhouse effect has been detected and climate change is happening now. We've seen additional evidence of this in the fact that the Arctic ice sheets are melting, wildfires are intensifying, and drought and flooding events are becoming more severe. We need action to change this, but we also need information. One important piece of the puzzle that we're missing is information about how aerosols affect climate change. Aerosols are these tiny little particles that are so small and light that they actually just float in the atmosphere, and they can come from a number of sources. These can include things like pollution, wildfire smoke, desert dust, or even volcanic eruptions. Now, aerosols are tiny, but they're really significant because they scatter and absorb the incoming light that's coming from the sun. Now, to our eyes, aerosols just look like a haze in the sky on an otherwise pretty clear day. And as a result of this acts as a sort of smoke screen for the Earth and causes a global cooling effect. There are a lot of unanswered questions that go along with aerosols that we need the answers to. Questions like how much aerosol comes from a volcanic eruption and how long is it going to stay in the atmosphere, or other things like how do aerosols affect cloud formation and cloud brightness. Now, the best way to answer these questions is to make measurements across the entire globe. And the only way that we can reasonably do that is from a satellite platform that has the ability to monitor the entire atmosphere all within a single day. The goal of my thesis project is to design a new satellite instrument to make the best possible set of measurements to answer these questions. The instrument is called the Aerosol Limb Imager, also known as ALE. Now, the word limb here refers to a side view of the atmosphere. Taking images from the side view lets us see how the aerosol change with height in a nice stable section of the atmosphere known as the stratosphere. Now, because the stratosphere is so stable, this means that the aerosols can last for a very long period of time, and therefore they have the greatest effect. From a satellite, ALE measures sunlight that is scattered back into space by these aerosols. Now, this scattering effect actually imprints the spectrum of the light with a lot of properties about the aerosols themselves. These properties include things like the size of the aerosols, the composition of them, as well as their distribution within the atmosphere. To measure the spectrum of the scattered sunlight, I've designed ALE to use a new technology that uses radio frequency waves to vibrate a crystal and bend the incoming light according to its wavelength. This lets ALE take many images at different wavelengths all in a very short period of time and without any moving parts, which is critical for a long lifetime in the harsh space environment. This is the prototype of the ALE instrument that I built here in the optics lab at the University of Saskatchewan with project funding coming from the Canadian Space Agency. My team and I are preparing for a test flight of ALE using a high-altitude stratospheric balloon to take the instrument into the upper atmosphere. The balloon flight will test the technology for a future satellite mission where ALE measurements will be able to give us new and improved information about the role of stratospheric aerosols in the climate change equation.